This is a very short review on AC, and I'm skipping a lot of material and concentrating only on the most useful things that concern us in this class, but be sure to read the whole chapter. When looking at an AC signal on an oscilloscope, what does the oscilloscope give us? It gives us the voltage in peak to peak. In this case, I have drawn a wave that is 10 volts peak to peak. What we really need now is volts peak. And from looking at the drawing then, volts peak is simply half of peak to peak, in this case 5 volts. Remember, it's the distance between the x-axis and the maximum peak voltage. So in this case, it's 5 volts. Volts RMS is found using the formula shown, which is that volts RMS is equal to 0.707 times volts peak. In this case, 0.707 times 5 volts, which equals 3.5 volts. And then the reason is that voltmeters are calibrated in volts RMS. When measuring AC, you're really measuring the RMS value. Now we can demonstrate an interesting relationship between AC and DC, that if I have a circuit that's 10 volts peak to peak in AC, that'll be equivalent to a DC voltage of 3.5 volts DC. And that means that both circuits will produce the same amount of heat when driving a resistor of the same value. Here is another waveform that at first appears to be AC, but if you notice, it never crosses the x-axis. That means that it never crosses zero, and so the wave never goes negative. So this is not AC, but in fact is pulsating DC. Another way to think about it is that we have an AC signal riding on top of DC. So we need to find that DC value, which we're going to call a voltage average. The wave goes as high as 35 volts and as low as 25 volts. So the average voltage is 35 plus 25 divided by 2, which equals 30 volts. This then is the DC level. We could say then that we have 30 volts DC level with a ripple voltage, and that the ripple voltage is calculated to be 35 minus 25, which is equal to 10 volts. So the AC signal is really a ripple with 10 volts peak to peak. If we have 10 volts peak to peak, that means we have 5 volts peak. And then we take and multiply that. 0.707 times 5 volts is equal to 3.5. So the RMS value of my ripple voltage is 3.5 volts. We use the RMS value of the ripple voltage to calculate the percent ripple. In this case, it's 3.5 volts divided by 30 volts, which is the DC level, times 100%. And we find that's 11.8%. Anything above 10% ripple is not good, especially when designing power supplies and other electronic equipment where the ripple voltage must be kept down to a very low level. Let's look at two sine waves now, A and B. Since A is to the left of B, that means that wave A leads wave B in time. And if we measure on the oscilloscope, we will see that wave A leads B by 90 degrees. These two waves will combine to create a new wave, which we will call the resultant R, and also at a new phase angle. We know that A leads B by 90 degrees and that they're both 120 volts. So we can form a vector diagram as shown above, where A is 90 degrees with respect to B. We use the Pythagorean theorem to calculate R when we say that R squared equals A squared plus B squared, or R is equal to the square root of A squared plus B squared, or 120 volts squared plus 120 volts squared, and take the square root, and so the resultant is 170 volts. We can find the phase angle by saying that tangent theta is equal to opposite or adjacent, or 120 volts divided by 120 volts. That means the theta is the arctangent of 120 divided by 120, or the arctangent of 1. So theta is 45 degrees. In conclusion then, the two sine waves have combined to create a new wave, which is called the resultant. It's at 170 volts and at an angle of 45 degrees, so it's offset from both waves. Also notice that I always say arctangent when other people say inverse tangent, but it's the same thing.